Thanks. So for the next half an hour, I'm going to talk about chemistry, or rather label graphs that represent chemicals. This, in the usual way you've seen, say, organic chemistry textbook. This is something that I've been, the result that I'm going to present is something that I've been working for almost a year now, and this is joint work with my supervisor Fabio Zanasi from also from UCL, and with Gale from Bristol, who is the chemist of this project, and also here in the audience. So the first slide is essentially the summary of the whole talk. So if people are very tired at this Friday afternoon session, if you want like a really high level overview, after the first slide, you can start, I don't know, zoning out and stuff. So okay, what's the motivation? The motivation is that in literature, especially on formalizing chemistry, and in the practice of organic chemistry and organic synthesis, there's two perspectives on chemical processes. One, I imagine most people, the first one, I imagine most people are fairly familiar with. That's the chemical reactions. If you open a random page from a chemistry textbook, you will probably see a lot of these. Like you put some things together, and the reaction is telling you what change those compounds are going to undergo. And that's somehow forward directed and predictive. It's used for storing chemical data, pedagogical purposes, and just reasoning about sort of forward chemical change. The slightly less well-known perspective are, at least for me, before I started this project, I was not aware of the so-called retrosynthetic disconnection rules that are hypothetical breakings of local bonds, and these are somehow backwards directed. Not read into the categorical analogy too much, this could be seen as a dual to the first one, in the sense that these are used by practicing organic chemists to synthesize organic molecules, in the sense that they look at something that they want to produce, then they identify some functional groups or some potential bond breakings of that hypothetical molecule, which they then go ahead and break, and then they produce a smaller set of, again, hypothetical molecules, and then they repeat this process until some known reactants, known compounds are reached. So yeah, somehow one forwards directed reactions, two backwards directed local disconnection rules. Okay, so what do we want to do with these? So I guess the contribution of this work is twofold. First of all, as far as we are aware, this is the first work where disconnection rules are taken seriously as mathematical entities. Like all literature I've seen of them is rather informal and more of like an intuitive guide towards what's going on, rather than formulas in its own right. For reactions, can I actually point with this? Okay, I'm just going to wave my hands. For the, oh yeah, I found the button. For the reactions, there's much more existing mathematical formalisms. Right, so that's the first one, and the second one is to prove that there is a very tight connection between the two. So the first one is that first what we're going to do in the talk is we define two categories corresponding to 1 and 2. Well, the first one is what we call react for reactions, and they're going to be represented as certain partial bijections that encode, I say, any physically feasible reactions, but that means in like really hypothetically physically feasible reactions. Like the only constraints we put on our reactions is that they preserve matter and they preserve net charge. So they preserve all of the atoms. No, in a chemical reaction, no atoms can appear or disappear, and net charge has to be always preserved. And number 2 is the disconnection rules. And okay, we call the category disc and the disconnection rules, but really, as you're going to see, it's bidirectional. So for every disconnection rule, there is a backwards connection rule that undoes it. then we prove that there is a very tight connection between the two. As I was saying, the theorem that we are going to get by the end is, first of all, that there is a functorial translation from disconnection rules to reactions, which is faithful, and moreover, it is full. Well, it's not quite full. It's full up to an isomorphism. Every reaction is isomorphic to something in the image of R. I'll talk about all of this in much more detail. Okay, now is the moment when you can zone out in case you don't want the mathematical details. So first of all, we represent molecular entities as labeled graphs. So yeah, the way this notation works is we more or less we just took it from existing literature, and it's quite standard in chemistry that these upper left indices represent the underlying set of the graph. The big letters represent the labeling, so the corresponding chemical, the atom that this vertex is representing, and the bonds represent the edges, I should say, represent the bonds. So here that would be a double covalent bond, single covalent bond, and an ionic bond is represented by a dashed line, and a charge, in case there is charge, is represented as an right upper superscript. There is this additional thing that the letter alpha always represents either an unpaired electron if it's connected to an atom, or a free electron, in which case it's not connected to an atom, but then it has to have the charge of -1. So yeah, if you see an alpha, think unpaired electron or a free electron floating around without being attached to an atom. Okay, first category is the category of reactions. And this is where I'm going to, I apologize to people on Zoom, I'm going to draw something on the blackboard. How the reactions are encoded, if you have two graphs that I'm going to represent by these big bulbs on the blackboard, reaction, as I said before, is a partial bijection. So in particular, it's a subset in this graph, call it A. So it's a partial bijection that does not need to respect any of the edge labelings. The only thing it's required to preserve is the atom labels. So in fact, if there are alpha vertices, so that if there are free electrons, it also does not need to preserve the electrons. So in this example, this is our subset. And in this case, the bijection is just the identity map. So this H1 goes to this H1. And you can see that over there, we have the plus, and here we don't have the plus. That's fine. Only the atom label has to be preserved. And okay, then there is, but this is not the category of partial bijections in the usual sense, because there is another condition that the rest is unchanged. So the complement of this set, and the complement of the image of the bijection on the other side has to be isomorphic to the original graph. That's this I there. Yeah, and then there is the additional condition that if something inside the set was connected to the exterior, to the outside, then it still has to be the case here. And if it wasn't connected to anything in the exterior, then it's still not connected to anything in the exterior. So somehow, oh yeah, and the extra condition, of course, that the net charge is preserved. Here you can see the net charge of the set is -2. And here the net charge is still -2 because now we have 3 minuses and 1 plus. So 1 plus and 1 minus cancel. Yeah, so somehow it's a combinatorial condition on the sort of the most liberal notion of what a chemical reaction would look like. How does the composition look like in this category? I have an example of that. So here we have 2 hydrogen molecules and 1 oxygen molecule that eventually, via some intermediate step, are going to react to produce 2 water molecules. and the first reaction is going to be represented by this. So what's happening here? We see that we indeed have a bijection. We have two O's here, and two H's here. And then here, as I said, the alphas may appear and disappear. So I'm not labeling them for that reason, because at the next step they're going to disappear. That's reaction number one. And then reaction number two, we're going to recognize like, now this one is another reaction. We have H, and O, H, and O here. So that's again a bijection between the non-electron vertices. So in the next picture, it's just the same equations that I drew in the same picture. And as we can see, there is an overlap between these, but that's fine. What we're going to do, because we also have this isomorphism of the exterior here, and isomorphism of the exterior here, which is going to pull this bit, this bit back to here, and push forward this bit back to there via those isomorphisms, and that's going to still give us another reaction. Okay, so once we've done that, we forget about the thing in the middle. We get a full new reaction that just starts from here and ends in here. And in this case, it's actually going to be the full molecules, because as you can see, they are already in bijection with each other. Okay, so that's all I wanted to say about the structure of the category of reactions. That's of course a formal definition. I don't think it's very useful to use our time here to talk about that. Now we talk about the disconnection rules. There's four of them, four disconnection rules. So we're still talking about the same sort of objects. So it's labeled graphs that represent molecular entities. So the first one, the first two are electron disconnection rules. Here for the first one, the condition is that the charge is strictly negative. So we detach an electron, increase the charge that was strictly negative by 1. And now, because we have detached an electron, it means a new unpaired. So the idea is that this one was paired with some electrons here, giving it a strictly negative charge. So now an unpaired electron must appear after this disconnection has been applied. For the second one, it's similar, but now the charge has to be non-negative. Now, non-negative charge together with a free, unpaired, sorry, not free, but unpaired electron. Now it becomes a free electron, and the charge is still increased by 1. As you can see in both cases, the net charge is preserved, because here we are adding a minus, and here we are adding a plus, and similarly for the other one. And the two other rules are even more intuitive, hopefully. This is an ionic bond between two things with the, if there is an ionic bond, the charge has to be the same for both atoms. So this one just removes the ionic bond. And this one is a n-fold covalent bond. Here we just decrease the n-foldness of it by 1. So it becomes an n-1-fold covalent bond. And we obtain an unpaired electron here and an unpaired electron there. Yep. So these we didn't come up with these disconnection rules. We just took them from the literature on organic synthesis. We just put them in formal mathematics as partial functions on graphs or local graph rewrites. Okay. So how do we generate this very syntactic disconnection category? We use these rules, and the terms that we are going to, so the objects are still the labeled chemical graphs. The terms are generated by these 5 elements, and I would say the only chemically meaningful one is really this 4th one. As you can see, for every D ranges over the disconnection rules. So for every disconnection rule, we have a term and a term going in the opposite direction. So here, this is the idea is that this one undoes the damage that this has done. So it's not really an inverse, and it's not an inverse precisely because we are going to interpret them as these reactions. So we need to keep track of which vertices have been touched, which vertices have been involved in a reaction. So if we do a disconnection and then a connection right afterwards, we're kind of getting back to where we started, but up to up to the fact that we need to remember that in this case, the vertex U would have been involved in the reaction, and therefore it's going to be this trivial change, but not the identity change. So it's going to be an idempotent, but not an identity. And the rest of the rules just really are there for mathematical consistency. We need identities because we want to talk about categories. Then this SU just says that the vertex U has been involved in the reaction while not changing anything. So for example, there's going to be an equation that says if you disconnect and then connect immediately back again, then you're just going to obtain the SU. That's what I was just talking about. And then because alpha vertices the alpha vertices represent the electrons can appear and disappear during the reaction, we need this rule that allows us to rename any electron vertex from U to V. That's hence this condition that V must not appear anywhere in the graph. And the last one is again to have the categorical structure. We need to be able to compose. So that's just putting things in sequence one after the other. So those are the terms. I apologize for the next slide because that's the equations. Yeah. Let me say very briefly something about these. Yeah, most of these are very intuitive. Like the renaming ones say that, okay, if you rename something to Z, then immediately rename Z to W, then that's just the same as immediately renaming U to W. That's just how renaming interacts with the rest of the structure. That's how renaming interacts with the different disconnection rules. This big box at the end here is a bunch of commutativity conditions. So it says when two disconnection rules can be swapped, like when the order doesn't matter between the two of them. So yeah, essentially when the equation is not one of these, it means somehow they obstruct each other and cannot be applied in an arbitrary order. Then this box somehow captures the symmetries of first disconnecting and then immediately connecting again in different cases. Yeah. So okay, we can put these equations on top of the terms. That gives us the category that we call disk, the disconnection category. Well, again, I call it the disconnection category, but really it's the category of disconnections and connections. Otherwise we wouldn't be able to obtain all formal chemical reactions. Okay, and as promised, there is a translation from disconnections to reactions given by the following. Again, I don't want to spend too much time on this. Yeah, essentially you collect into these sets all of the things that have been involved in a reaction. Here you notice that the vertex that appears as the right superscript doesn't actually appear here in this case, in the case of the covalent bond breaking, ionic bond breaking, or the well, here it doesn't actually exist, so that's fine. So for these, it's possible to sort of cut out the set very finely without touching the unnecessary vertices that shouldn't be involved. And then the bar of every the barred version of every connection rule, of this connection rule. So the connection rule is interpreted as the reverse. Oh yeah, I forgot to mention that both of these categories have a dagger structure. So this one just says that the dagger is taken to the dagger. The dagger in the reactions is hopefully quite obvious because there's a bijection and an isomorphism involved. So just swap the sets, and take the inverses of the bijection and the isomorphism. All right, so that's the translation. Oh yeah, I have an example of how it looks, the translation. So here we have some very syntactic manipulation of a very tiny molecule, namely oxygen with -2 charge. But I think this might not be the best example because I'm not sure if oxygen has this kind of behavior, but I'm just treating it as sort of a formal structure at this point. So we start with something that has 2 negative charges. apply 2 times the electron disconnection rule for strictly negative charge to obtain the oxygen radical with two unpaired electrons, and then we have two free electrons floating around. So I keep saying free electrons here, but I mean unpaired electrons, and 2 free electrons floating around, and then we can still keep applying electron disconnection rules until oxygen has charge +2, and now we have 4 negative electrons floating around. And these are the corresponding translations from the disconnection rules to the category of reactions. And this is how the composition looks like. So here, for example, we essentially pull back this V because it doesn't already appear here, and we cannot pull back the Y and V, well, because they're not in this set, so they're not to be pulled back. And I mean, and they don't appear on this side anyway, because they're precisely created by the application of this rule. Right. So and then we do symmetrically on the other side. So we obtain this composite reaction. All right, and with this we can wrap up with the sort of big results. So first is soundness. That one is hopefully something that if I gave you the mathematical definition, then anybody from this audience could just sit down and show that the equations are indeed preserved. So it's indeed a Dagger functor. So every one of these horrible list of equations that we saw a couple of slides ago is indeed preserved and valid in reactions. It is complete in the sense that R is faithful. So just to spell it out very explicitly, for any terms as defined above T and S, they are identified by this translation R just in case, if and only if they are in fact equal under these equations that we saw a couple of slides ago. And we have the universality result, which is this almost fullness. Well, almost in what sense? If we have a reaction, then there's always a sequence of disconnection rules. There's always a sequence of disconnection rules starting from A, but not necessarily ending in B. Because remember, the disconnection rules can never change the names of vertices in A. So it's really from a chemist's point of view, it's a bit silly, but I guess we want to be precise here. So we start from A, end up in some B prime that is isomorphic to B, and moreover this isomorphism and composing this translation of the sequence of disconnection rules with the isomorphism gives us back R, the reaction that we started from. Okay, and with that, I want to talk about what do we actually want to do with this, and with this we also conclude. So there's 3 sets of future work questions: chemical, computational, and mathematical. The chemical ones are the important ones, I guess, because we want this to be useful for actual synthetic chemistry. So how to incorporate stereochemistry? This is not unclear. So that's the spatial structure of the molecules. Like at the moment, it's just connectivity, and how to incorporate that at the local rewrite rule level is not super clear to me. What's a bit clearer is how to incorporate the notion of energy or dynamics into this. Like you could think of perhaps that each disconnection rule has an associated cost of transition, perhaps context dependent, and then that cost could represent the probability of transition or energy. And then another question is this notion of composition. It's somewhat related to double push-out graph rewriting. That's where I take the inspiration from. But is it really appropriate for representing chemical reactions? The computational questions is actually something we are intending to work on this summer. is to actually implement like this is the algorithm that turns the universality algorithm, the one that takes a reaction and reproduces a sequence of disconnection rules, is very syntactic. So it's super ugly but easily implementable on a computer, and the completeness result relies on the normalization procedure, which is likewise very algorithmic. So both of these are implementable on a computer. So this is something we are intending to do. And of course, when you combine these two, you get essentially a unique canonical form for every reaction as a sequence, as a certain sequence of disconnection rules. And then the mathematical questions are: what is the categorical structure of reactant disk? Like we came with this applications first approach to this. So so everything's kind of defined by hand. Okay, they both are dagger categories, but what else? What else is going on in terms of category theory? If somebody is able to spot some nice categorical structure there, let me know. Well, oh yeah, this is I already alluded to. What's the precise connection to double push-out graph rewriting? That has something to do with the composition of reactions as well. And finally, it's kind of unrealistic to assume that all of these disconnections happen one after the other. In fact, in reality, some of them will probably happen at the same time. So that also relates back to the more chemical questions: is how do we model the monoidal structure of this? And with this, I thank you for your attention. Questions? Okay, that is.
Thanks for the talk. I'm wondering if there's any like disconnection rules out there. Do they have something special mathematically?
Can you say it again?
Disconnection. They have something special like
I want to say no, because I mean the way you obtain this is you really think about the chemical intuition in terms of where the electrons go, how do you disconnect bonds, how do you connect bonds. So
and do they themselves form some sort of do they have some these four rules themselves have any relation of actually?
Again, well, in the sense that some of them obstruct the application of others. That's the only thing I think I could say, because otherwise, like for example, you could imagine that okay, you really need to apply this first if you want to start disconnecting these electrons, but otherwise they acting on very different entities, right? So only in the sense that not all of them commute, but that's very vague as a mathematical structure. Yeah. Can we is it time for?
There's one more question.
Yeah.
What is an isomorphism in disk?
An isomorphism in disk. That is an excellent question. I actually think that probably the only isomorphism in disk are the identities. Yeah, because actually that's true, because the moment you touch anything else, you kind of just stuck. You like this notion of composition is sort of cumulative. It just keeps getting larger and larger. So yeah, the only isomorphisms in disk are the identities. Yeah.
Very quickly, Leo, how do you get the qualities that you have?
How do I get these? I mean, these somehow encode the symmetries about somehow if I disconnect this electron and then I do something with it, it's the same as if I disconnect this electron. So essentially, I sat down, I looked at a lot of cases, and like, oh, this should hold by symmetry of graphs. So somehow this encode symmetry, or like some combinatorial symmetry of these graphs. Yeah.
Yeah. I was asking that because some of these they will be like energetically viable.
Yeah.
Some of them not.
Yeah.
So
yeah.
probably this whole table is parameterized on data.
I see. Yeah. So maybe you can put some distances on these equations or something like that. Yeah. Yeah.
Also, because chemical reactions not always follow these these process addition.
Mm-hmm. Cool.
Okay.
Yeah.
There we go.